Okay, I'm going to give you here the clearest introduction to differential equations that I can. Now I want to be clear, this is an introduction. It is by no means the everything about differential equations. I'm going to start out with a familiar example. Imagine you've got a spring and you have a mass attached to that spring. So we've got a mass with mass m and a spring with constant k. Imagine that this is on a plane with no friction whatsoever, and we're going to give that mass a pull and let go and watch how it moves over time. This is a familiar example. You learned it as simple harmonic motion. Now we're going to model this using a differential equation. To start off with, we're going to write out everything that we know. If I give that a pull, so that I've stretched that spring, let's say a distance capital A, and then I let go, my initial position, my x value when time is equal to 0, is A. That's how far I've pulled it from its rest position, and we'll call its rest position our origin. The second thing that we know, that's always true, is Newton's second law, F equals ma. So force is equal to mass times acceleration. Now what is the force on this? According to Hooke's law, the force is k, the constant, multiplied by the distance the spring has been stretched. And notice it's going to be in the opposite direction of the direction where we actually stretched it. See, if I pull it this way, let's say we make this positive. So that's the positive x direction. If we pull it this way, the force is going to be that way. And it's going to be equal to k times x. So our force is negative k times x at t. X at t is our position at time t. And when I multiply k by our position from the spring's rest position, I get the force. That's equal to mass times acceleration. Well, mass is mass. Acceleration is the second time derivative of position. You see, velocity is the first derivative of position. It is the rate of change of position with respect to time. That is the very definition of velocity. Acceleration is the rate of change of velocity with respect to time. So acceleration is the second derivative of position. Force is position times k, because with a spring, if we're at position 0 when the spring is relaxed and we pull it a distance a, so our initial position is a, we're going to get a force of ak going the other way. So this is our differential equation. We call it a differential equation because it's an equation that involves differential elements and or derivatives. And because we have a second time derivative here, that's a differential equation. Now it's time to come up with a solution to this. So to start off, I'm going to rearrange it. I'm going to divide both sides by mass, and I'm going to have them switch spots. So let's just make them switch spots. So we have mass times the second derivative is equal to negative k times x at t, or the second derivative is equal to negative k over m times our position. So just a little simple rearrangement there. Now, as we try and come up with a solution to this, the process we're going to use, and we'll get into more sophisticated methods as the equations get tougher, but we're going to use our experience. We're going to look at this and try and think from our experience of something that we've solved or done that looks familiar to having the second derivative equal to the negative of the first derivative times some number. So it's sort of a guessing, checking process if you think back to, say, factoring trinomials from knowing products. All right, so from looking at this, and again to recap, we start out with a situation where we've got a mass and a spring. We take Newton's second law. We know that the force comes from the spring and it's proportional to our position. And from Newton's second law, acceleration is the second derivative of that same position. That's what gave us this equation in the first place. Now, as we try and solve it, from looking here, we can see that we have the second derivative is equal to something times the actual function. So it's something like the second derivative is proportional to our function. Well, to understand this better, let's consider an example. What if the second derivative was equal to the function? When have we ever seen this? So you have to remember back to having learned to take the derivatives and the second derivatives of various functions. And if you recall, when you took the derivative of sine, you got cosine, and when you took the derivative of cosine, you got negative sine. So what that means is if x at t is the sine of t, or, so we've got sort of two candidates, two possible answers here, or if x at t is the cosine of t. In either of these situations, the first derivative is the cosine, or in this case, the first derivative is the negative of the sine, and the second derivative and in this case, the second derivative is negative cosine. However, in both cases, look at this. The second derivative of x at t, when x at t is the sine, is the negative sine of t. So the second derivative is the negative of the function you're taking the derivative of, both in this case and in that case. So either of these functions will work if all we're looking for is the second derivative to be equal to the function we started out with. But we're kind of similar to that, except we've got this slight difference in that the second derivative is the negative of some constant multiplied by the function we started out with. So although these are good candidates, they're not exactly perfect. All right. What if, and of these two, which do you think from this situation, from experience, are we heading towards? Remember, the sine of t looks like this, and the cosine of t looks like that. Now, when time is 0, remember from our situation we started out with, we gave that a pull, so we've moved the location of our block from its starting position at time equals 0 when we let go and the system kind of started to unfold. That makes it this one, not this one. So although both of them work in terms of the second derivative being the negative of the original function, should have had a negative there. Although both of them work for the second derivative being equal to the negative of the original function, only cosine has us start out displaced from our initial position. So we're going to go with that. Now, what if we have our position as a function of time equal to the cosine of some constant number times time? Then our first derivative is a cos a t, a negative sine at, And our second derivative is negative a squared cos at. So if we multiply time by some constant number, when we take the second derivative, we will end up with the negative of the square of that constant times time. Now remember what we're going for. What we're after is we want the second derivative to be equal to the negative of k over m times the function that we start out with in the first place. So we need the negative k over m to take the place of a squared, or negative a squared, sorry. So let's try, what if a squared was k over m? Then that would make a equal to the square root of k over m. Now when we piece this together, x at t is equal to the cosine of a, which is the square root of k over m times t. So we're almost there. Now when I take the second derivative of this, my second derivative with respect to time is going to be equal to negative root k over m times the cosine of root k over mt, which is the negative of k over m times the cosine of root k over mt, which is negative k over m times the function we started with in the first place. So we are satisfying Newton's second law, where acceleration times mass is equal to our force. The only thing that's missing is when we started, we moved this a distance of a. Remember, at time 0, our position was a. We call that initial conditions. For those initial conditions to work, all we've got to do is multiply this by a. You see, if we make x at t a times the cosine of the square root of k over m times t, because when you take the derivative of a function times a constant, that's the same as the constant times the derivative. Everything's going to come out the same, except we've got that multiple of a there. So let's give this a try. We now find our first derivative as negative a root k over m sine root k over m t. And our second derivative is negative a k over m cos root k over m times t. And if I just get these two to switch spots, you'll see that that is equal to negative k over m times x at t, satisfying the required differential equation. And I'll just rearrange it back. I'll multiply the m up here, satisfying the original differential equation of f being equal to ma, which is what all the mechanics side of physics comes down to. So to recap, we start out with the situation. When we give that a pull, we write down our initial condition and Newton's second law. We then understand that the force from Newton's second law here, well, the force comes from the spring, is equal to this. And mass times acceleration, well, acceleration is the second derivative of that very position that's giving us the force. That's our differential equation. We rearranged it and then had a close look by inspection and said, wow, the second derivative is equal to the original function. It's just made a negative and multiplied by some number. I've seen that before. And then we thought back and said, oh yeah, we saw that both with our original function being sine and cosine. Again, that just comes from experience of having taken the derivatives of many functions. That's why you studied calculus, partially. So after working our way through there, we found the one that makes the most sense in this situation. And then we modified it to get that constant to come out. So it ended up being a number we just multiplied the variable by. And then we multiplied the whole thing by a constant at the very end to satisfy our what we call initial conditions. This is an initial value problem. So I realized there was a lot of guesswork and it was based on experience. I'll do the exact same problem again, except using a thing we call Laplace Transform, which comes from a very rich bit of math involving complex analysis, very interesting stuff, actually developed by Leonard Euler. But this is sort of the gist of setting up a differential equation and then using your experience to come up with a reasonable solution and then modifying that solution to match exactly the initial conditions of the equation that you wrote down.